So what is SALC? See, SALC is symmetry adopted linear combinations. Okay. As I have mentioned in the definition, if you will see, SALC is basically what it is. It is the linear combination of basis set composed of the stretching vector of the molecule. Means what? It is something like, if you will see that in any geometry there are the two variables, minimum two variables are there. One is a bond length, another is a bond angle. So if you will make the vector component of it and you will add bond length with bond length, bond angle with bond angle, then you will generate some sets, right? So if you will make them in the linear combination, it will give you the SALC. So for what purpose it is required? So basically, SALC is helpful for determining the scheme and symmetry. For example, you might be knowing in case of tetrahedral and octahedral, what we used to say that in case of tetrahedral, splitting of D energy level will be T2G and EG. Or whenever you are making the MOT diagram of octahedral complexes, mostly the level of different orbital will be at ATE. A means A1G, then T1G, then E1G, right? Then why A1G? Why not others? So these many symmetry used to become from the SALC. Okay. Moreover than that, which orbital is going to be combined, like in a crude way, what we used to say, px, py, pz. So pz is going to be combined with pz, and with respect to that, anti-bonding orbital is going to come. That is a basic thing, right? But it might be possible that there will be a comparable energy, and in that case, pz can be mixed up with higher energy orbital. These many information used to become from the SALC. Second, it helps, as I already told, it's helpful for the binding scheme and symmetry. Now, how do we calculate the SALC? Actually, there are the two methods. One is called project operation method, which is purely based on stretching factor. The moment I will say stretching vector means it is going to combine only bond length. Okay. Now, the second one is the basis composed of irreducible representation of stretching mode of the molecule. So I will tell you both of them, but we shall start today with the project operation method. Okay, again, why do we should study SALC? SALC will give you the information in what way your MOT of the given molecule is going to be look like. Like what we have learned, first we will classify the molecule depending upon their point group. Then with respect to the point group, there will be a character table. From the character table, we will apply reduction formula and we will come across with the irreducible representation in terms of vibrational, rotational, and translational. And then we will come across with the Raman active and IR active. So these many informations are basically correlated. Now, among them, which are going to make the MOT, these informations used to become with SALC, and which factor is going to be contributed more. We will discuss later on. So let us move one by one. So the next one is project operator. What is projection operator? See, projection operator, if I will make you understand with terms of analogy, so always remember, suppose you are having some illuminating materials, right? But that material will illuminate only when the light is going to be projected on it. Did you get it? So first, what you need some light source, then illuminating material, and whatever the illumination is going to become, that will become on the surface. So three things are required. One is a source of light, then you need illuminating material, and with respect to the illuminating material, we need an object where that illumination is going to take place. So similarly, that information, yeah, source of light is character table, right? Illuminating material is project operator, and after project operator, whatever the information is going to become projecting on the screen, that is MOT, that will be vibrational mode, that will be transitional mode, that will be breathing mode, that will be umbrella mode. So well, various names are there, but now we can understand what is the importance of projection, right? So if you will see, I have written an operator always act on something, right? Now, normally on atomic function, on the vibrational basic function, the symbol is square bracket F, which means operate on. right? For example, we used to make some kundali. For that, what we need a computer, and what other things are required, those are timing, right? So the beautiful prospect about the kundali is we need computer, we need to operate, then only you are going to the informations of for the future. So same way, operator means to commute two things at a simultaneous position, that will be called operator. So this is the projection operator formula, where it is equal to 1 by h summation of chi irreducible q in a bracket dot q is the function. As I told, square bracket means operate on. So this particular factor will correspond that these symmetry elements are going to operate on this with the help of this one, right? Irreducible representation, you might be knowing, in any character table, the characters which are present in the symmetry element, as I said, those are called as chi irreducible representation, right? Then symmetry element q, and in with respect to that qf, they are going to be operate. Here I have mentioned h is the number of operation in the group, q a particular symmetry operation, right? F is the operate on, I already mentioned here. Chi ir is the character of irreducible representation under the q symmetry element. So if you will see, this project operator formula is very much similar to reduction formula. But the only difference is that reduction formula produces the number. However, the projection operator produces the functions. That may be vibrational modes, that may be MOT, that may be binding symmetry, that may be a destruction of symmetry as well. Okay, so many informations are going to be come through projection operator. For the reduction formula, always remember you will give only the information of the reduction in terms of various factor, right? But here you will give the information about the functions. Now let us start with ammonia molecule. I have skipped the water one. If you want, I can tell you later on, but we will start with ammonia molecule. It is big with respect to water and big tricky as well. So ammonia pyramidal, this is the shape. So how many symmetry elements are present? E, 2C3 and 3 sigma Vs are present. And this symmetry element correspond to the point group C3V. This is the character table, right? In the previous slide, I was telling these are the characters of irreducible representation. Characters, right? These are irreducible representation. This one is a point group, and these many are the symmetry element. And these 2 and this 3 in front of sigma v, this will correspond to the number of symmetry element. Always remember, this information is not required in case of projection operation formula, but it plays crucial role in case of reduction formula. So be cautious when you are using projection formula, don't use this. Otherwise rest of the things are quite similar, but if you are using reduction formula, you are supposed to use this. Okay, we will go move now. See, to operate the projector formula, what in the very beginning I told you what you are supposed to do. Suppose you will take water molecule. In case of water molecule, what you will do, every atom is going to distinguish in different axes, means x, y, z. So for example, in case of S2O, how many axes we are going to see during the symmetry element? Total 9 axes are there, right? Then I told you that it is bit difficult when we are moving towards a complicated molecule. For example, if the number of atom is suppose 7, in that case what we'll do is 21 axes are going to rotate, and with respect to that you are going to find out. It is a bit difficult. Then in the next presentation I told you, okay, so now what we will see, we will see the number of atoms which are going to be unshifted, right? And their contribution is already fixed to make it simplify. And further, if we will move, what we have told that forget about anything. Now we will focus one by one to the bond length and particular bond length. As I told, in case of cis N2F2, we need to focus NN bond, we need to focus NF bond, right? So this way we are going to reduce the complications and came across with some information. Now I'm telling that whenever you are going to find out the projection formula or the SALC equation for the molecule, you should focus only on these two things, bond length and bond angle. I guess these is well aware to all of you. Bond length, like in ammonia, how many bonds are there? Three bonds are there. Three NH bond is there. An angle, bond in between of the two bonds is called as bond angle. Now, I mentioned ammonia molecule has three bond length and three bond angles. Two you can easily be relocated out. Third one is the beyond that. Okay, I will let you know. So here I have shown you. Suppose this NH molecule, I have categorized it as S3, to make it distinguish. Otherwise, if I will say, suppose in C3 NH bond is moving, all NH bond will start move, you will not be able to conclude whether the changes are going to happen or not. So to make it more easier, what I have told, that NH bond, you can, this NH bond is S3, NH S2, and this NH is S1. Now see, it is not compulsory that you are also make it as a component of S. If you want, you can make it as R1. If you can make it as R2, if you want, you can make it as R3. It all depends on you. Even there are the books who prefer sigma as a notation. So this is called sigma 3, sigma 2, sigma 1. But to make it smooth, I made it as S, because sigma is also a symmetry element. In that case, it will be quite confusing. Now see, here it is a bond angle, right? See, here I have shown ammonia as a planar molecule to make you understand, but it is not planar. Always remember, not this way. This H will come in this way. Here it will be lone pair, right? But how many how these three angles are going to be? This one, and this one. But in real molecule, if you will see, I will tell you. See, this one is one bond angle. This one, second one, and this one is the third one. This one, one, two, and then three. So total bond angle is 3. If you will see, this is, if I will add this H with this H like this way, so this is somewhat with respect to this H. If you will see, the geometry will be umbrella. I will use this word, always remember. So see what I'm doing, I'm going to add these H. Okay. Okay, now see, if you will use this H, this one, and this bond is like this. If I will rotate like this one will be umbrella. But this angle is out of the plane, always remember. So the any movement around this angle will be called umbrella motion. I will use it, but I'm making you here to make it understand how this umbrella mode used to be work. Now we will move next. Okay, so as I told you, now our responsibility is, we came to know that how many internal coordinate are available in case of ammonia molecule. One is bond length, another is bond angle. This is bond length, this is bond angle. In angle, I have given the representation A1, A2, and A3. If you want, you can write it as θ1, θ2, θ3. It all depends on you that which projections or which notifications you are going to use. But during the examination, make sure that the same notification should be used throughout. If I'm using S3, S2, S1, then it should be same for whole molecule. It is not like that in between you are using S3, later on you are going to use sigma. It will be quite confusing. That's why you make it practice of your own choice that which symbol you are going to use to represent this. This is S3, S2, S1. It might be R1 or R2, R3. It may be sigma 1, sigma 2, sigma 3. It all depends on you. So now, what is our first duty? We will work on first on bond length. So what we will do, we will see during the symmetry element how many number of bonds are going to be unshifted here, right? So I have written tau S NH. So during the symmetry element E, how many bonds are going to be unshifted? If we will see, E means 360 rotation. If any molecule is going to be rotated with 360, you are going to get the same molecule. So all the bonds are going to be unshifted. So the value of E will be 3. Okay. Now we will operate on 2C3. Now see, in case of C3, what is that? This is the principal axis. This one is the principal axis, right? This one. And you are going to rotate it. Now, if you will rotate, what would be happen? S1 will become S2 and S2 will become S3. Am I right or wrong? And this S3 is going to become S1 during this C3 operation. I will repeat. S1 is going to turn up S2. S2 will turn up S3, and this S3 is going to turn up as S1. So in short, all the bonds are going to be shifted. That's why C3 contribution, if you will see, it will be 0. Now, sigma V. How many sigma V are present in ammonia molecule? I told you 3. How come it is? One is along this way, this one. Another is along this one. And the third one is along this one. Right? Now see, if you will pass the plane through S1, you see here, like this way you are passing the plane, right? So what would be happen? This S2 will become S3 and this S3 will become S2, right? The only thing which is not going to be changed is this bond S1. That's why the contribution will be 1. Okay, again I will repeat it. You make it as a practice now. E means you are going to rotate the molecule with the angle of 360. So any molecule which is going to be rotated 360 means nothing is going to be changed. But here we are going to see the bond, right? So how many bonds are there? 3. So all 3 bonds are not going to be rotated during the symmetry operation E. That's why we will write it here 3. The next option is C3 symmetry element. C3 means the principal axis passing through this, right? Now, if you are going to rotate the molecule through this axis, what would be happen? S1 will turn S2, S2 will turn S3, and this S3 will turn S1. All the bonds are going to be shifted during this C3 operation. That's why the contribution will be 0. In sigma V, we have to first find out how many sigma V is there? 3. Now see, how come? One is across this way, another is across this way, and the third one is across this way. These 3 bonds are there. Now we will pass the sigma V from this plane. What would be happen? These 2 are going to be shift because mirror plane, no. So these are going to be shift. So now S2 will be S3 and S3 will be S2. But what about this one? Since the sigma V is going to pass through with this way, so in that case, what we'll say, it is going to be unchanged. That's why the contribution will be 1. Now, see, this is the character table of C3V point group. This one you have calculated. Just now you have calculated that in case of C3V through NH bond, how many bonds are going to be unshifted during the symmetry element. And this is the reduction formula which I have taught you in the second lecture. Here, if you will see, this K is present. But if you will compare with the projection operation, there is no K. So be careful. Again, I am telling. First, to form the SALC, you need to reduce by applying the reduction formula, and later on projection will come. Don't add directly projection operation, otherwise you are going to get a wrong answer. Again, I will repeat what I have done. For any molecule, you need to find out the reduction formula with respect to bond length or bond angle, the reduced form, right? So here I have, in case of ammonia, bond length is NH. First I have make sure this reducible representation, then we will operate on reduction formula, right? So like I'm going to operate on A1, right? So according to the reduction formula, 1 by H, what is H? H is the order of group. So here, if you will see, order of the group, kya hota hai? Order of the group is basically the number of symmetry element present in the particular point group. So if you will see, how many E are present? 1. How many C3 are present? 2. And how many sigma V are present? 3. So in short, total symmetry element present in C3V point group is 3 plus 2 plus 1. So it is C. That's why 1 by H value will always be 1 by 6. I have written here, right? Now it is K. See, in case of K, basically what is that? It is the coefficient which is present before E or before C3 or before sigma. Okay, if you will see here, the coefficient which is present is 1. So we have written 1 out. Chi IR and chi R. Chi IR is irreducible representation. This is reducible. So chi IR, if you will see with respect to A1, what is the value? It is A1. So I have written A1. Chi R, it is 3. So I have written here as a 3. Right? See, K chi IR dot chi R. Chi IR correspond to irreducible representation, and this one correspond to reducible. This is the your reducible one, and this is irreducible one. So if you are going to project the formula, how it will be look like? 1 by 6, 3, 1, 1 plus. Let us apply on C3. How many values for K? It is 2. This 2. Then A1 1 1, and then reduction formula, then it is 0, right? Similarly for sigma V, 3 1 1, right? If you will solve it, you will come to A1. Now we will apply same thing on A2. In that case, if you will see, again same procedure we need to follow. 1 multiplied by 1 multiplied by 3 plus 2 multiplied by 1 multiplied by 0 plus 3 multiplied by minus 1 multiplied by 1. So overall the contribution will be 0. Now for the last one, NE, 1 2 3 plus 2 minus 1 0 plus 3 0 1. So these two subsets are going to be 0. So 3 1 2 6 by 6, that is E. So I can say the irreducible representation for a NH bond will be A1 plus E. Always remember, this irreducible representation can be obtained only through NH bond. Okay, but if you remember, we have calculated 2A1 plus 2E. What it was? It was the involvement of bond length as well as bond angle. Just compare with the previous lecture. Here we are talking only about bond length. That's why it is A1E. We will also explore with respect to the bond angle, but it will become later on. So first, tau NH is going to be A1 plus E. Now let us verify whether our answer is right or wrong. So what we will do? See. Now see, this informations you got, you have reduction, right? Now you know the A1 value, but you got that tau NH is equal to A1 plus E. So if this information contains A1 plus E, so if you will subtract the A1, then the information should be present that should be belongs to E. So what we'll do, 301, right? In case of A1, we have written as it is, we are taking from the character table. Now if you will reduce these two, now reduce it. So 3 minus 1 2, 0 minus 1 minus 1 1 1 0. So that is 2 minus 1 0. Now if you will compare with the character table, see 2 minus 1 0, and this one correspond to irreducible representation E, right? So it means that this reduction is right. Did you get that or not? Clear now? So let us move. Okay, now we'll come on projection operation. Again, I'm repeating, for any molecule to frame the SALC equation, first you need to reduce, apply the reduction formula, and whenever you are reducing, you are going to vary only two internal coordinate, either bond length or bond angle. Suppose if you are going to operate through bond length, in that case you apply reduction, and then you will come across with the reduction formula, right? And then we are going to apply project operation. Okay, so this ammonia molecule I have shown you for the reference that how this symmetry element looks like. This is C3, sigma 1, sigma V1, 2 and 3. Now in case of projection, always remember it is differ from the character table. So now what you are supposed to write in character table, if you remember, it is 2C3 and 3 sigma. But whenever you are going to apply project operation, you need to segregate these C3. You need to segregate this sigma v. Since E is 1, so there is no mean of segregation. That's why we'll write it as E. But here it is 2C3. So in that case, what we'll write? C31 and C32. Similarly, in case of sigma V, what we will write? Sigma V1, sigma V2 and sigma V3. For all molecule, you have to operate the same technique. And the technique is that you are going to segregate all symmetry element. Similar like ammonia, here 2C3 is there, so we are writing as C31 and C32. And 3 sigma V is there, so we are writing sigma V1 and sigma V2 and sigma V3. Okay, so now the what we have done, I have mentioned here, each symmetry operation must be individually identified, need to compute the effect of each operation explicitly, and no k in the projection operator equation. Focus on this, no k, but this k will be present in reduction formula. I have already classified the bond with S1, S2, S3. Okay, this is S1, S2, S3. Now, what we will do through symmetry element, we will see what changes are going to happen. As I told, it is 360, so no one is going to be changed. So we'll write S1, S2, S3 as a same way as it was earlier. Now C31, this is C3. Now you are going to rotate the molecule along this way, right? I can tell you how. See what you are going to do. This is your C3. Okay. Now you are going to rotate the molecule through this C3. Right. Now, if you are going to rotate this C3 axis, now what would be happen? See, what would be happen? If you will see S1, क्या होगा S1 का? S1 will come here. Now see, I have written here. Right. Now S2 will be shifted here. I have written here. And this S3 will come S1. Now see, this S3 will become over here. So now 3, this is S3. Right. Now let us say for C32, the moment you will start moving the C32, now in what direction you will say? Say first you have done this way, now you will do this way. Okay, so again what will I do? C3 is same this way. Rather than to this way, now we will rotate the molecule is in this direction. Okay, so now rotate it. What would be happen? This S1 क्या होगा इसका? Now S1 will turn up to this S1. If you rotate it, it will come in this direction, right? So that's why we have an S1 here. Now S3 will switch to S2. So this is S3 and S2 will be lie down here. That's why it is S2. So I have shown you few of them, E and C3. For sigma V, I would suggest that you make it as a homework and perform and notice that what changes you are going to get it during the mirror plane sigma V. Okay, next. Now, see, this is the thing for ammonia molecule. We are taking the molecule in this way. So now, what we are supposed to do? We will going to apply project operation. So during the E, now see, it is going to operate on which S1. I told you whatever is written in the bracket that will correspond to project on. So here the information is going to become across the S1. So what we are going to focus, we are going to focus on this one. Okay. So during the symmetry operation E, now what S1 is going to be changed? Nothing is going to be changed, as I told you in the previous slide. S1 is going to remain S1, right? So what we will write? S1. In C31, as I told earlier, C31, S1 क्या हो गया? S1 कहाँ गया? It is going to become on S2 position. So what we will write? We will write S2. Now C32 is the anti-clockwise rotation. In that case, S1 is going to sit on the position of S3. So we will write S3. Now similar way we will make the practice for sigma V now. Now sigma V1 I told you this one. And this bond is basically what? S1, right? So now this is passing through this. So according to mirror plane, what changes are going to be happen in S1? If you will see, no, nothing is going to be changed. Why? Because the only changes are going to happen on this S2 and S3 bond. It is going to be unchanged or unshifted. That's why we'll write it as S1. In sigma V2, if you will see, this is sigma V2. This is sigma V2, right? So what would be happen? Now S1 is going to sit on the position of S3. So what we will write? S3 here. Now in case of sigma V3, if you will see, this is the plane, right? So which is going to be unshifted? It is S3. But here the whole projection operator is going to operate on S1. So we will only focus on S1, what changes it is going to happen during the symmetry operation. So this is sigma V3, right? Now S1 will change to S2 and S2 will come S1. Since we are focusing on S1, so what we will write it here? Its position will be S2. Okay, again we will make it as a practice. Now see, projectron operation formula is going to operate on S1. So we will only focus on the changes which are going to be happen on S1 during the symmetry operations. So during the symmetry operation E, what would be happen? The molecule is going to be rotated with 360 angle. So you are going to the same molecule as it was initial. That's why S1 will be remain S1. S1. C31 means you are going to rotate the molecule across the C3 axis in clockwise direction. So in clockwise direction, you are going to rotate. In that case, S1 will come here. So what the information is going to be now? S1 is S2. In case of C32, you are going to rotate the molecule in anti-clockwise direction. Okay, so in that case, what would be happen? This S1 will be seems like S3. So we will write S3. Sigma V1. This is sigma V1. So sigma V1 occupies what? S1, right? So no change is going to be happen. That's why sigma V1 contribution will be S1. This is sigma V2. So now your mirror is passing through with this axis. So what would be happen? This S1 will be lie down on this. So that's why in sigma 2 contribution will be S3. Now this is the last one, sigma V3. If you will see, this is the sigma V3. So what would be happen? These two are going to be exchanged. So S1 is going to be S2. Now next. See, this informations you have find out just now. And this is the A1. This is has been taken from character table C3b. It was all one. It is a symmetric, no? So like in 2C3 it was mentioned as 1. So what you have done, you have make it as C31 and C32. So in both the cases you will write 1. Always remember, right? In sigma V also it was 1, but how many sigma V are there? 3, right? So here also you will write 1. For each sigma V you will write 1. So the next step is the multiplication of QS1 A1. So S1 multiplied by 1, what it will information will come? S1. Again S2, S3, S1, S2, S3. In short, nothing is going to be changed after the multiplication of 1 with a positive sign, right? So now, this is the projection operation formula where it is written as 1 by H summation of chi irreducible representations Q operate on particular bond vector. Here QF is S1, right? Q is A and chi R you have operated. So if you will see, this multiplication give you this much. The summation of all this will give you the information of this particular informations. Okay, so next is 1 by 6. Right, what we have written, we have added because it is a summation symbol. So S1, S2, S3, S1, S2, S3. Okay. Now The next is 1 by h. So 1 by h, again you know how many rotations, symmetry elements is there? 1, 2, 3, 4, 5, 6. Right? Now, in that case, it will be 1 by 6. If you will solve this, the information, then 2s1, 2s2, 2, 3, 2 will be common. So 1 by 3, s1, s2, s3. Remember, this is the equation for A1. Okay? So this is totally symmetric stretching, if you will see. Right? Now see, this is a stretching mode, right? Now this H are moving out, and to encounter this movement, nitrogen will be moved in opposite direction. So totally symmetric, right? Now the same thing we will make it for E vibration. Why we are operating only on A1 and E? See, remember, you have first reduced the character table with respect to the NH bond, and on applying the reduction formula, you came across that tau NH is A1 and E. So your main priority should only be to apply on A1 and E, right? So A1 you have finished. Now we will learn for E. See, E vibrational mode, S1, same thing, right? Now E, same thing, we have taken it from character table. So in character table it was 2, -1 and 0. Right? So 0 correspond to with respect to sigma v. That's why I have written 0 for all sigma v here, -1 for all C3. Now you will make multiplication. So it will be 2s1 minus s2 minus s3 0 0. Now we will operate on projection formula. So what it will be? Summation of these three. So 2s1 minus s2 minus s3 written. How many symmetry element? 1, 2, 3, 4, 5, 6. So it is 1 by 6, 2s1 minus s2 minus s3. That is for E. And earlier it was for A. Okay. So A it was 1 by 3, s1 plus s2 plus s3. For E it is 1 by 6, 2s1 minus s2 minus s3. Okay. Now the another question we used to ask, that why we are operating only on s1? Why not on s2? You can do it, but you will get the same information. That's why we are focusing only on one bond. Like we have focused on s1. The same informations you are going to get it for s2, same information you are going to get on s3. Okay. So now this is the representation of E mode. Okay. Now if you will see here, what would be happen? See, this NH is moving in this direction. However, this is moving in this direction. So this is asymmetric stretching. Right? Now, see, E means what? As I told you, E corresponds to degeneracy. Degeneracy means two different modes are having the same energy, then it will be called as degenerate. So now E vibration is degenerate. As I told in the definition, there should be a two mode which should have the same energy, but you got only one. Here you have find out only one, so it means that another will also be there, and that particular mode will have the same energy as this one. Okay, so now E vibration is degenerate in nature. Degeneration means two vibration with exactly same energy. See, if two different vibrations are having the same energy, so in experimental, rather than to see two different spectrum, two different peak in a spectrum, you will notice only one. And of course, if I want to put any comment about the intensity, then the intensity will be high. Why? Because two mode are going to be merged at a particular place, so the intensity is going to be increased. So correspond to observation of one peak in the spectrum, but with double intensity. So first E mode, which you have find out, it's very easy just to operate the projection operation, and you will get one E. But the second one is a tedious one. Okay, and there are the several ways to find out the second one, but whatever the mode you will get, it should be orthogonal to the previous one which you have got it from easier way. Always remember. Okay. Otherwise, I will tell you that in what way we should proceed. Now see, this you have received. I have not used 1 by h here for mu NHE. See, one if anyone will ask the mode, then you will write it as 2s1 minus s2 minus s3. You don't want to focus on the contribution. 1 by 6 is the basically contribution. Okay, so mu NHE is 2s1 minus s2 minus s3. Now what we are going to do? We are going to get second E vibrational vector function, right? So always remember what should be there. What you do, you will operate this C3 on this. Here C3 means, always suppose if you are moving towards the higher molecule where the principal axis rotation is C4 or C5 or C6, then what you will do, you will rotate this function, yeah, operate this function with respect to C4 or C5 or C6. Means higher Cn should be preferred if two axes of rotation or more than two axes of rotation are present in a point group. Luckily here only one type of axis of rotation is present, that is C3, so you can opt it either C31 or C32. It all depends on you. I have opted C31, but suppose if you are operating this on hexanuclear molecule or octahedral geometry, in that case you need to find out with respect to C6. Okay, so here let us start again, come to the point. Now we will, what we'll do, through C3 we will operate on this function, right? So now see, one by one we'll see. C3 on 2s1, C3 on 2s1 क्या होगा? Now S1 क्या हो जाएगा C3 के बाद? S2 हो जाएगा, right? C31, again I will tell you what is C31. The movement along the C3 in a clockwise direction. So I am projecting here. Okay, this is C3 clockwise direction. Okay, so now what would be happen? This S1 क्या होगा? ये S1 क्या हो जाएगा? It will become here. Okay, so basically this S1 is going to be S2, so you are supposed to write S2 here. Means actually it should be S2 here. So now S1, this S1 is going to change as S2, but whatever the coefficient is present, you are going to use the same one. So here it is plus 2, so you will write plus 2s2, but you will write the S2 just below the S2. Don't write it here. Okay, again I will repeat. C3 on projecting on 2s1, what it will be, forget about this 2 first, you should focus on S1. So S1 is going to be S2, so what you will write it as here, this S2 first you will write it here. Okay, now the second point you should supposed to write is the coefficient which is present. It is 2, so you will write it as 2. Here it is plus, so you are writing as a plus. Okay, now we'll move towards the S2. Now what would be happen for S2? See, this S2 is going to be sit here. So in that case, what would be happen? S2 will be S3. So what we will write? S3 here. But as I told you, as it is, it should be written. So here it is minus. That's why you are writing here as a minus. Okay. Now the last one is S3. Now see this S3. S3 is going to be in the longer way as S1. So here you will write it as S1, but since it is minus, so you will write it as a minus, right? What is this? This is basically the operation of C3 on this earlier E vibration vector function. Okay, so now you will subtract these two equations. So what it will become? It will become 3s1 minus 3s2. You will take it as a common, 3s1 minus s2. So only mode, if I want to know, then you will say S1 minus S2 is also right. But if you want to SALC, always remember in what way SALC used to be work. SALC is basically work on 1 upon root of square of the coefficient of all the symmetry element present. Like here you have written 3s1. So what it will be? 3 square plus इसका 3 square. So what would be 1 upon root 9? Okay, so in that case 3 square 9, 999, so it will be 18. So in 18 you can write it as, in what way you can write 18, and the above side it will be 3. So if you will solve it, it will become 1 by root 2. Okay, now this is the depiction for second E mode. Now see, these two H are moving towards the same way, and this NH is moving in the same way. Okay, now, so SALC equation S1 comes 1 by root 3. See, how come it is 1 by root 3 now? See, projection operation is different thing. In that, what you are supposed to write, you are supposed to write 1 by H, right? So if it is 3 by 6, so you will write it as 2 by 6, so it is 1 by 3. Whatever you are going to get it, you make it as a root. Otherwise, what you are supposed to write, your function is S1, S2, S3. So what you should do it, I will tell you. Wait, to find out the SALC equation, you should write 1 upon, wait, for this I am writing, it should be upon root of coefficient square of this coefficient. So here it is 1, so it is 1 square plus, in case of S2 same thing, right? So it will be 1 square. In case of S3 it is also the same one, right? So what you will write, 1 square. So what it will come across, it will become across as 1 upon root 3. Hope it will be very clear. And this 1 upon root 3, I'm going to use it for this SALC equation. Okay, so for this one, if you want to say what it will be, I will solve it. 1 upon, same, first you will make it as square root, right? Then the coefficient is 2, so means 2 square plus, for S2 what is the coefficient? It is 1, so it will be 1 square. For S3 what is the contribution? Again it will be 1, so what it will write is 1 square, right? So what it would be, 1 upon root of 4 plus 1 plus 1. So overall it will be 1 upon root 6. And this thing I'm going to use it over here. Is that clear? Now, always remember here I have written S3A. Okay, I will tell you why. Now, this is S3B. Why it is S3A, S3B? Because it belongs to E category. Remember, this one is for A1, this one for E. That's why I have written 3A and 3B, means belonging to the same category. The only variation is A and B. Okay, so this was across the bond length. Now, we will start for second internal coordinate, and that is bond angle. Now, how many bond angles are present? I told you 3, right? One in between of the two NH, and another is the beyond in the umbrella one. So in that case, if you are going to apply the reduction formula, so during the operation E, whether the angles are going to be changed? No, that's why the contribution will be 3. In case of C3, of course, they are going to be changed. Why? This the big one, side one is going to be changed. So in this case, it will be 0. In case of sigma V, it is 1. Okay. Again, you will apply on the reduction formula and you will get A1E. Same information which you have obtained during the bond length, you are going to get it as bond angle. And now I will flash back. In case of ammonia, if you remember, you have find out that tau vibration is equal to 2A1 plus 2E. And just now, when you have operate through the reduction formula across the bond length, bond you got A1 plus E, and across the bond angle also you got A1 plus E. If you will add both, then what will be? It is 2A1 plus 2E. What does it mean? It means that vibration mode is comprised of bond length as well as bond angle. In another mean, I can say that the IR active mode are involved in the ammonia molecule comprises due to the changes in bond length as well as bond angle. And more precisely, I can say both stretching and bending mode are present, because bending mode used to be come through angle, but stretching mode come through bond length. Okay, sure. So here I have added A1 plus E. See, one way is that since you got the same type of representation as you got it in a bond length, right? Then you perform projection operation and you get information. If your beginning is same, then of course last one should also be same. No? So there is no need to solve. That is a one way to approach. Second way of the approach is, no, we will do it one by one. We will see whether both the informations are same or not. I can tell you both. So here I have opted directly. Right, the first, since A1 is responsible, right? A1 is the symmetric mode. So in case of symmetric mode, the wave function should also be same. So that's why I have written 1 by root 3 S1 S2 S3. But rather than S1, I have written S2. This 2 correspond that this functions has come from angle, and 1 correspond that this one comes from bond length. Okay. In case of E, if you remember, there I have written S3A. Here I will write S4A. And this one is S4B. It means that they are coming from E. Okay. Now see, if you want information more insightly that whether these mode are coming from in plane or out plane, then I'm going to explain in the coming slide. But if you don't want, then it is all okay. This much knowledge is sufficient enough, and it is beyond the scope to go more inside. But for your knowledge, I'm going to put it. At least for ammonia molecule, you should be able to know that which one is in motion, which is out of the plane. Rocking, twisting, scissoring, and bending. These 4 modes are there, right? So in that case, you should know that which are in plane and which are out plane. Okay. So now see, I've written here the in plane motion. I will use the word breathing vibration. Okay. Okay. The breathing vibration has same reducible representation and distribution of the vector as the stretching motion. Therefore, they will have similar function, as I told you. Since you got the same information like A1E, so of course they will have the similar functions. So no need to repeat projection process. But we can write the equation for E mode only directly. Why not A1? Always remember here this A1 is redundant. This A1 is not because of in plane motion. Huh? This is meaningless. Redundant means it is something like inefficient or unnecessary thing. So it is something like noisier, okay? So A1 is a redundant mode, because if the molecule was planar, then all H and H cannot be closer at once. Of course, now if the molecules are planar, then in case A1 cannot be changed, no? So it is not going to provide any information. So the total symmetric mode in breathing motion is not allowed for physical reasons. So here this A1, of course, for bond angle, this information is right. But don't think that this A1 is coming from breathing motion. Okay. See, in bending also there is different type of pattern. One is a breathing mode, which is this way, matlab in plane motion, and another is out of the plane motion. That is umbrella. I have told you where I have taken the outside of the angle, right? I will tell you. Now sketch the projection. So this information I'm going to give you on the basis of the previous one, right? So if you will see this E, what is that? 1 by root 6, 2S1 minus S2 minus S3. In short, I can say this S1 component is having higher impact with respect to S2 and S3. Or I can say in the magnitude way, this S1 is more. That's why this S2 and S3 are going to subtract. So it will be expanded. Whenever you are making the projection, be careful. This mode, wherever you are showing this, it should be expanded, and these two should be contract. So now see, I have written here this one. If you will see this one, right? So this one will be expansion, and now these remaining two will be contract. See, I have written as it is S1, S2, S3. Actually, I should write it as theta 1, theta 2, theta 3, or A1, A2, A3. Okay. So don't be get confused. It's wrongly written here. It should be theta 1 minus theta 2 are A1, A2, A3. Okay. So it is A1 expand, A3 and A2 are going to contract. So in that case, you see, that's why I have compact these two. Now see, these are going to be compact, right? But these two are going to expand. Did you get these two? If you say they are here, these are going to expand, but these two are going to compress. So with respect to this one, if you can say these H, forget about anything. This H, this one, and this one. What they will do if they are going to expand? So it means that they are going to compress this one, right or not? So in that case, what main effect is going to happen is that this H star is going to be contracting more. So here if you will say H star is this one, this is contracting, right? This H is going to contract, right? And this H is going to expand this way. Okay, so this one is P mode. Now elimination of redundant mode. See, you got to know that through the angle the tau NNH should be A1 plus E. Even you get the information for E also. One E you got it, so second E is not difficult. As I told you in the bond length, you are going to get it. But still, the problem is that which A1 is going to become. Since I told you that in motion, A1 is not allowed, symmetric is not allowed, right? So now see, tau vibration is 2A1 plus 2E. This 2A1 means tau is stretching plus tau bending. Tau is stretching, you have calculated, it's A1 plus E. Tau bending, A1 plus E. Now, tau bending means tau breathing and tau umbrella. Now, tau breathing, as we have just now proved it, it is only E. So, undoubtedly, tau umbrella will give you the information about A1. Now, see, I've written also only two E modes are allowed. So, we have already found both of them earlier in plane motion. So, the active mode will be A1 symmetric bending, and that should be come from umbrella. Now, umbrella mode, vector used for out of the plane motion should be single arrowhead. That is a depiction mode. So if you will see, this is out of the plane. Now see, how come it is umbrella, I will tell you. Why we call it as umbrella. Now see, if you will see this B3 and B1, they are going to be out of the plane. And even this one, B1 also. Now you depict this, right? And this one is what? This one is the handle of umbrella. So if you will see, so this is total umbrella. So the movement which takes place due to the out of the plane will be called as umbrella motion, and that will correspond to the NH out of the plane mode. But another which is in plane, it is called breathing. See, breathing, there is a reason to use the word breathing. Breathing means it is something like, if you will remember, one is going to be expand and another is going to be contract, right? So in case of expansion, what we use to term we are going to use, it is going to breathe, right? Undoubtedly for another one it is apoxia, right? But popular word is breathing. Here the popular word is basically what? Umbrella. Why it is umbrella and why it is breathing, always remember. Okay, so determine the reducible repentance. Same thing will become 301 A1 plus E. This is the depiction for A1. A1 you have already solved it in case of bond length, and that was 1 by 3 S1 plus S2 plus S3. So in case of angle, what it will be? 1 by 3 theta 1 plus theta plus 330. This is projection equation. Okay, but if you are going to frame it for what you call, if you are going to make it for bond angle, it should be 1 by 3. Here it will be B1, B2, B3, or you can write it as theta 1, theta 2, theta 3. So these are the SALC equation across SN1, SN2. See, SN1 is for bond length, SN2 for bond angle. Okay, this is S3A again for bond length, bond length, bond angle, bond angle. Okay, and these four will become from E. So now you can calculate how many mode I have shown it here. Total, if you will see, I have shown it here 2, 4, 6. Now, what was tau vibration? In earlier slide, I have told you 2A1 plus 2E. Okay, 2A1 plus 2E. 2E correspond to how many? 2. So 2 multiplied by 2, 4 plus 2, yani 6 mode, right? And the 6 mode we got it here, right? So, and even you can find out for ammonia, it is bending. So the formula will be 3n minus 6. So n is 4, 4, 3 minus 6. So total 6. So we got it all 6 equation. This is the representations of A1 and E. And that's all from my